All right, thanks. So, there we go, good. So at the Non-Volatile Systems Lab at UC San Diego, we've been doing some work in redesigning transaction mechanisms for new storage devices based on emerging non-volatile memory technologies. So I'd like to acknowledge my co-authors, Trevor Bunker, Mir Schwartz, and this work was done with professors Rajesh Gupta and Steve Swanson. So transaction systems typically rely on write-ahead logging algorithms like ARIES, which were designed to maximize performance for disk. But emerging non-volatile memories, things beyond flash memory, have very different performance characteristics. And so if we apply those existing algorithms as is to these new storage devices, we get disappointing performance. So today I'm going to talk about a system we've designed called MARS, which is a new write-ahead logging scheme designed to provide the same features as systems like ARIES, but none of the disk-related design decisions or overheads. And so MARS is based on a new storage device primitive, which I'll present, called Editable Atomic Writes, that make transactions more efficient on these new solid-state drives. So today, we have flash memory. It's ubiquitous. It has its problems, but it does pretty well. But it's going to get harder and harder to use. And on its heels are a series of new memory technologies. There are things like phase change memory, spin torque MRAMs, memristor. And with these new technologies, we can build memory devices that will have very different performance characteristics. So they'll be nearly as fast as DRAM. They'll be nearly as dense as flash memory. They'll be non-volatile, and they'll be more reliable than flash. And so with these technologies, we can then use them as DRAM replacements for main memory, or we can use them to build faster storage devices. So this will be really critical as both DRAM and flash sort of end near the end of their life in terms of device scaling. So let's look at the impact on storage performance that these new technologies are going to have. So in this graph, I'm basically showing performance relative to disk. On the x-axis, we have 1 over latency on a log scale. On the y-axis, we have bandwidth on a log scale. And we'll start with disk down here in the corner. And we'll start the clock at 2006 when flash SSDs started appearing. So in 2007, we got PCIe-based SSDs, like one from Fusion IO. That gave us about 100x performance improvement over disk. A few years later, we built one of the first PCM-based prototype SSDs in our lab. It did a little better on bandwidth. It was actually a little worse on latency, but these were really early PCM chips, so they weren't that good. A more recent flash drive from Fusion IO gets us even more bandwidth. And then in the next year, we'll see PCM devices where we can now build an SSD that should give us almost 1,000x the performance of disk. And then a few years later, we should be able to put these memories on the memory bus, and then we'll have several 1,000x performance improvement. And in this progression that I've shown over 10 years, we're seeing about a 2.4x improvement in performance per year. So that's a bigger improvement than Moore's law. So it's really a big change in performance and the way storage now looks to the rest of the system. So the problem then is, how do we take advantage or realize the potential of these new memory technologies? So we have a bunch of these new memories. We can build a very fast storage device with low latency and high bandwidth. We can take the existing software stack. We can optimize it to make access to storage fast. But then we have a bunch of applications that were still optimized for disk. So for example, if I want consistency guarantees in my application, like I want to do an update to this tree and I want to know that it's going to be safe in the presence of failures, I need to use a write-ahead logging algorithm. So I need to first write the data into the log on disk, and then I need to update it in place. So it turns out these write-ahead logging algorithms like ARIES were designed for disk. But now we have a highly optimized storage system. It has very different performance characteristics. And so we want to re-examine the design of ARIES. So to start, here's a new storage architecture for NVMs. So in our lab at UCSD, we built a prototype SSD called Moneta. So Moneta has a bunch of FPGAs inside, It has a storage controller, and that distributes requests to a bunch of memory controllers over a high bandwidth ring. And then the host talks to the device over PCIe. Now, with Moneta, there were a lot of overheads in the software stack that we had to deal with just to get decent performance out of our devices. So we have an optimized kernel driver and device interface where we try to target a lot of the overheads in the Linux I/O stack. And then we have a user space driver where we offload some of the work of the file system into the hardware so we can eliminate the cost of both going into the OS and the file system on the common case. So with that, we get a very fast device. So for a 512-byte request, we can do that in just 5 microseconds, and we get about 1.8 million IOPS of throughput. So we use Moneta as a platform to now re-examine ARIES. And let's start by looking at the characteristics of Moneta as compared to disk. So we get very good, raw performance improvements. We're about 1,000 times the performance of disk. Now, random writes are just as cheap as sequential writes. So, we have a lot of software that's optimized for sequential writes, and that may not be as effective. We also have a much more flexible interface to the device. So we're no longer stuck having to do block requests. We can access data at the byte level if that's the amount of data we need to access. In Moneta, we now have a lot of parallelism. So we have many memory controllers, and we can have many outstanding requests at a time, so we can do lots of concurrent I/O. And then finally, these devices are going to be interesting because they're typically going to have a bandwidth mismatch. There's going to be more bandwidth across the memory controllers internally than there'll be between the host and the device. So that's really an opportunity to actually offload work into the storage array to better take advantage of that bandwidth. So previous work to support transactions isn't a good fit for SSDs like this for 2 reasons. It either targets a different storage technology, or it doesn't integrate well with existing software. So on the one hand, we have a set of systems that were designed for disk, so they made those optimizations, things like write-ahead logging, shadow paging. There's also been a few projects that have tried to put atomicity and durability support in the disk controller. And then on the other hand, we have a set of systems that have tried to provide transaction support for non-volatile main memory. So things like recoverable virtual memory, Rio Vista, later work like Mnemoscene and NV heaps, which targeted technologies like PCM on the memory bus, and they provided more programming support for a persistent heap abstraction. So for that reason, those things don't integrate well with existing software because they really support a different model for storage. And then lastly, you have a group of systems designed for flash-based SSDs. These are probably most similar to our work, but they're not a good fit because they've typically targeted applications with much simpler transactions than complex schemes like ARIES. Also, their implementation is flash-specific, so most of the intelligence is in the flash translation layer, so that would make them difficult for ARIES. So we choose ARIES because it's probably the most sophisticated write-ahead logging algorithm that's used commonly in databases today. And so ARIES, like with any system, there are really a set of features that ARIES has to provide to its applications, and then separate from that, there are basically a set of design decisions that we make with ARIES in order to maximize performance for the technology that's currently available. And these are really 2 separate things. So we're going to sort of do this deconstruction of ARIES where we'll first look at the features that it has to provide to support ACID transactions, and then we'll look at the design decisions it makes to get good performance with disk. So here's some of the features ARIES provides. Not all of them, but some of the relevant ones. So for example, it provides flexible storage management. It provides fine-grained locking. These are things that let ARIES support objects of different sizes and support highly concurrent operations on those objects. It supports partial rollbacks via save points. So that makes transactions more robust and efficient, and you can help resolve deadlocks that way. And ARIES supports recovery independence, so you can recover parts of the database even if others are in error. And it supports operation logging, and that gives you high concurrency lock modes and helps basically optimize performance on index structures like B trees. So these are some of the features of ARIES. Now let's look at the design decisions that guided its implementation for disk. So basically, ARIES is optimizing for sequential writes. So for example, it uses a no-force policy to write back data. And what that says is that, okay, ARIES is going to basically flush the redo log entries to disk at commit. And by doing that, they're guaranteed to be updated in place later, and you can do it when it's more convenient. So that basically gets those synchronous random writes off the critical path of committing transactions. Another optimization is a steal policy. So basically, ARIES allows the buffer manager to write back dirty pages before a transaction actually commits. Now, you can do this at a little bit of a cost. So in addition to redo log entries, you have to write undo log entries to disk before you write any of those dirty pages back, so you can roll back if you have to abort. But that creates a lot of opportunities for ARIES to actually do larger sequential writes and eliminate some random writes. It's also critical because it makes transactions scalable, because you can basically reclaim buffer space as you need it. And it also helps avoid false conflicts for small objects. And those conflicts come from the fact, actually, that ARIES is based on the idea of pages. So all updates to storage are at the unit of pages, and page writes are considered to be atomic. And they do that so that it matches the semantics of disk, and it makes the recovery and buffer management implementation easier to. And then finally, ARIES uses log sequence numbers. So basically, every update to a page is given a unique number to provide ordering on those updates. And that can be used at recovery, and it can enable higher level features like operation logging. So it turns out that this set of design decisions, they're great for disk, but they're not great for fast SSDs. So we built MARS, which is a new version of ARIES that we've designed specifically for fast non-volatile memories. So in thinking about how to do this, we thought, okay, well, we could implement all of ARIES in hardware. That would certainly be fast, but it would be complicated, and it would be it wouldn't be very flexible. So what we decided is that let's only implement the things in hardware that we need, or the parts that are expensive. So we came up with a new storage device primitive called Editable Atomic Writes that will basically let us get the same features out of MARS as ARIES, but without any of the disk-related overheads. And so to implement this, we've basically provided atomicity and durability support in the hardware. On top of it, we provide a very flexible interface for implementing transactions, and then we use that to build a simplified piece of software to replace ARIES, and that could integrate into existing storage managers. So let me explain the interface and how it works. So consider some sequence of writes in your application that you want to happen atomically and durably. So I have this set of operations. I want them to be atomic. So I would do a bunch of writes to the log. And I would basically specify where those objects should be written into the log and where they should finally be written atomically into the storage array. So I write objects A, B, and C. And then this sequence of operations, I just happen to hit this conditional where I might want to actually update the object A again. And with editable atomic writes, I'm actually just going to edit it in place. So I'm going to update what I've already written in the log. And then when I'm done, I'm going to commit the operation. And then that's going to happen atomically because the storage device is actually going to copy these things in place and be able to recover in case of a failure. So what we do with this interface is we basically give applications the ability to access and edit the log prior to commit, and they get to manage the log space, control where objects go, and basically treat the log now as really an extension of the application's storage space. And then we have the hardware actually do the copying of the data in place to take advantage of the large bandwidth we have internally in our device. So let me now talk about the implementation by going through the same example again, but showing you the details. So I won't present the whole interface. I would actually refer you to the paper, but these are just some of the commands we implement. So I've recoded that example. Now we do a sequence of log write operations, which tell the device to copy data from memory to the log, a commit operation, and then internally a write back gets executed. And we also have support for abort and partial aborts. So with this example, first look at the storage array. And the way it's laid out is we have a transaction table where we have an entry per transaction ID or transaction that we can have in flight in the system. This is managed by the storage device. And then the log is actually split into two pieces. So there's a metadata region and there's a log region. The metadata region actually holds entries, one per logged object, that tell you things like the target address for that logged object and its size. And then the log file, of course, holds the actual logged objects. So we start off by doing a log write. We specify an address in memory, an address in the storage array, and an address in the log. The system allocates a transaction ID, marks it as pending, points it to a metadata entry, and then we can copy the data into the log and update the metadata entry. And so we do that for each object, and now we have a linked list of metadata entries, and they basically give us access to all the logged objects in this transaction. When we hit this conditional now, instead of doing a log write, we're actually just going to modify the log directly with a regular write to the address of A in the log. And now we can commit. So commit will ensure that all the log writes have completed. It'll mark the transaction as committed, and at that point, it's guaranteed to complete. So internally, the device will do a write back operation where it'll traverse the metadata entries and copy the data in place. And then it can free the transaction ID. So what we've done here, which is different from previous systems, is that we've actually separated the metadata and the log data. Now you couldn't or didn't want to do that with disk because then you would have to seek and it would be a huge performance penalty. But here it's actually to our advantage because now we can control the logged objects and where they live, and we can read them and update them as many times as we want. And so that actually makes them contiguous, and so they're in the same format, whether they live in the log, in memory, or in the rest of the storage array. So with editable atomic writes, now we can build MARs, and we can revisit each of those design decisions for ARIES. And so instead of using no force, for example, now we're going to actually just rely on the hardware to write data back at the memory controllers themselves. So we take advantage of the internal memory bandwidth, and we actually eliminate extra PCIe requests to write the data back. Instead of using Steal, the hardware is going to do the in-place updates, and we're actually going to be able to still retain the benefit, well, at least the scalability benefits of Steal, but we can eliminate the undo logging, and we can just rely on the log to actually hold the latest copy of the data. So if we have to evict an object from the buffer pool, we can just read it back in later from the log if the transaction hasn't already committed. Instead of using pages, software will actually operate directly on objects, and the hardware will actually manage the layout of those objects. They may have to be striped across controllers, but software doesn't have to worry about that. And now we only need to pay for the amount of data we actually need to access. And then instead of log sequence numbers, we're going to actually have ordering be maintained by the hardware. So the hardware is going to assign a unique commit sequence number at commit for each editable atomic write, and we can use that at recovery time to apply things in the correct order. So with editable atomic writes and MARs, now we can get the same features that we got with ARIES. So we can get flexible storage management, we can get fine-grained locking, particularly because we're not going to use pages, but we're just going to operate on objects directly, which is going to simplify our software quite a bit. We get partial rollbacks because our device actually supports an abort operation where you can give it a pointer into the log that you want to roll back to, and then you can continue executing from there. We get recovery independence because we can actually, our recovery team can scan metadata, and it can check if there were errors on objects and then recover only the ones that are still available. We don't currently implement operation logging. It's something we could do. It's not clear if it'll have as much value here because we operate on objects directly and don't use pages. So now I want to go over the hardware architecture. This is the controller implemented in the FPGAs for Moneta. And I've highlighted in yellow boxes the ones that we either updated or added to support editable atomic writes. So requests come in this region on the left. We have a PIO interface for requests and completions. They come in through a request queue. We have a transaction ID manager to assign a transaction ID. And then they go to a scoreboard. And the scoreboard schedules and orchestrates the execution of everything in the controller. So it handles DMA transfers to and from the host, and it handles basically distributing these log write, commit, abort, write back operations to an array of memory controllers. So storage is striped across those memory controllers, and in front of each memory controller we have a logger module that basically implements those atomic write commands on that particular chunk of storage. So imagine a little transaction ID table, metadata section, and log at each of those loggers. And so these two things participate in a two-phase commit protocol. So the scoreboard can send a commit, say these 3 loggers were involved. They would mark their TIDs as committed when the log write's complete, send an acknowledgement. Now we can tell the device we've committed, and we know that no other request can execute until the write back occurs. And then each logger will make its local copy, mark the transaction ID as free, and send an acknowledgement to say it's done. So with editable atomic writes, we get a big latency advantage over traditional multi-phase write algorithms. So we show latency here in microseconds for a 512-byte request. And I've broken it down into hardware and software component. So basically, that's time to issue the request, do a DMA transfer, do the request in hardware, and then complete the request. So to make this atomic in software, we would actually do a write to the log, a commit record write, and then a write back of the data. So it takes 3 times as long. In our system, we could do this with a log write command followed by a commit. So then it's just 2 I/O requests, and it's actually only 1 DMA transfer now because commit is an instruction that our system understands. It doesn't involve transferring any data. And since this is actually a single piece of data we're writing at 1 memory controller, we actually don't need to coordinate around that ring, so we can do it as 1 atomic write instruction. And notice that we can overlap the write back of the data with the completion of the request in software. So we're about at the same latency as regular writes, and we're up to about 3 times faster than doing logging or atomicity in software. We also get a huge bandwidth improvement. So this shows bandwidth for various access sizes. You can see that the bandwidth of soft atomic is half that of writes because we're having to basically write twice as much data. We have to write to the log in addition to the in-place locations. With editable atomic writes, we roughly track the bandwidth of regular writes, and we get up to 3.8x the throughput of these other approaches. So that source of improvement is really our ability to utilize the internal memory bandwidth. So this graph shows the total bytes read or written across all the memory controllers internally. So for regular, have the same internal and external bandwidth for regular writes. For soft atomic, we have the same bandwidth as regular writes because we saturate the PCIe bus, but half of that goes to writing to the log. And then for editable atomic writes, we get much better utilization. We're about 5 gigabytes a second, and we get 3 times the bandwidth of these other approaches. So we used editable atomic writes to implement some other applications. If you use them in a straightforward way, you could implement the same applications as some of previous work in atomic writes for Flash. So for example, we implemented a persistent key value store. So we took Memcache DB, which uses Berkeley DB, and we basically swapped that out with a hash table that we wrote using editable atomic writes. So this shows updates to the key value store for a varying number of client threads. They're all running on the same machine as the server. And we have an unsafe version. It just does regular writes, and then we compare to soft atomic and Berkeley DB. So we're only 15% slower than running without any safety guarantees, and we're over 1.7 times faster than soft atomic. So finally, let's look at a comparison of Mars and ARIES. This is a simple experiment or micro benchmark where we basically we do a bunch of atomic swaps of random pairs of objects from a large table. And we measure this for a varying number of threads for both Mars and ARIES. And what we really try to do with this experiment is just measure the impact of using Mars and editable atomic writes instead of using ARIES and the traditional no force and steal policies. So with that, we get up to 4 times the throughput improvement, and we get better scalability as we increase the number of threads. So existing transaction mechanisms like ARIES were designed for disk, and we've built Mars to redesign those write-ahead logging algorithms to take advantage of the characteristics of these new storage technologies. So we're able to provide the same features as ARIES, but without those disk-related overheads. And we do that with a new primitive we've designed called Editable Atomic Writes, which is really a generic primitive for implementing atomicity. So with it, we're able to simplify software. We're able to make the log accessible and editable prior to commit. And we can minimize the cost of atomicity and durability, make them essentially free by offloading logging commit and write back to the hardware. And with that, we get a 4x performance improvement over ARIES. We can reduce latency by up to 3x, and we can reduce the required host-to-device bandwidth from anywhere to 2 to 3x. So thank you, and I'll be happy to answer your questions. Is that me? Cool.
Sudarshan, Georgia Tech. I was just wondering if any of the read and writes, since they go through the memory controller, do they go through the processor cache?
The reads and writes. Oh, yeah.
So in your first slide, you mentioned that the cost of sequential reads and sequential writes and random writes is same. So would the probability of making random writes increase the cache miss, and so the cost wouldn't be the same?
But I mean, it really depends on your application, right? Whether or not you'll have random writes. I mean, there's no, and I think the cost of the cache miss relative to the cost of going to storage, it doesn't make a huge difference.
So would you be able to comment on like the amount of cache misses these applications, at least something like Memcache DB suffered?
Oh, I see. Well, Memcache D doesn't necessarily have much locality per se, so we're not looking at applications with a lot of sequential locality anyway.
Phil Bernstein, Microsoft. One of the features of ARIES is that it also provides archive recovery from media failures using the very same algorithm and the very same log. Have you given any thought to how to address that problem without adding yet another mechanism on top?
Yeah, it's definitely something we've been wanting to look at more and implement. I mean, it seems like we could still do it using editable atomic writes. I mean, as long as we maintain this log, this history, and it's something that we can and that we can checkpoint occasionally, I think it would be possible, but we haven't done it yet.
Harumi Kuno, HP Labs. When you compared your performance to ARIES, was that ARIES with a buffer pool and DRAM, or was that ARIES just running against NVRAM?
No, that's sorry. Yeah, that's ARIES with a buffer pool and DRAM. That's right.
Thank you.
Yeah.
Mark Ulbridge, also from HP Labs. So it appears you have to find the temporary data in the middle of your transaction. How does that work with a transaction that modifies, say, 100,000 records?
Oh, sorry. Can you repeat?
So as your transaction's running, you make temporary copies, and if you want to change those copies, you have to find them again because you're not changing them in place. How do you do that lookup? Is that a hash table? Is that fast?
Oh, right. Yeah, we're assuming it would be a hash table. That's right.
Yeah, Luis Pedrosa from the University of Southern California. I'm not an expert in non-volatile storage, but my understanding is that disk-based hard drives have the whole seek problem, so random access is slower than sequential access. But with flash memory, sequential reads are more or less uniform. It doesn't matter what you're trying to read, it's all the same. But writing, it basically has to delete the page and then overwrite it. So if you write twice in the same place, and by chance it's cached, so it's actually faster because you're only actually writing the thing once. And so I understand this is just a change in the read and write patterns and speeds. Do you guys just assume that all reads and writes are uniformly fast or slow? Reads being faster than writes, of course. Or is there any way to take advantage of the particularity of writes?
Well, so unlike Flash, there's not going to be such a huge read-write asymmetry, and you can just update in place because these technologies will have greater endurance. So it's not really necessary to always kind of do this.
You don't have to write the whole page all at once.
Right. No, you don't. If you need any wear leveling, it'll typically be implemented like in the memory controllers themselves, so you won't, as the programmer, won't see it or have to worry about it.
Thank you very much.
Along this, I'm Tom Boyle from FutureWay Research Lab. Along a similar question of his, although the programmer doesn't have to see these wear leveling and processes and things, if there's an interruption in the middle, there's damage. If you have a crash, the effect on the data is unrecoverable. And my main question, and I may have missed something very important that you said, but you basically said you would have A, B, C in the log, and then you would edit A in place. Now, usually you have to erase something. If you had a crash, you lose A. If you fully erased A and started to proceed to put A prime in there, if you crashed, you would lose both A and A prime. Did I miss something on your discussion on that?
So we don't have to erase before we write. We can just write directly. And if we crashed when we were writing, we wouldn't have gotten to a point where we committed this editable atomic write. And so we wouldn't apply those changes anyway.
But you wouldn't have A anymore. The code that put it in place.
The copy of A in the log, though, right?
The copy of A in the log and the code that put it there is gone, so you can't get that back either. No?
Okay, well, I'm not sure I understand what the problem is then.
We take this one offline?
Yeah, I'm happy to talk to you.
Okay.
Peter Desnoyers, Northeastern. So yeah, this is really interesting. What I was curious about is the role that the controller plays here, and in particular, is this approach still feasible for, a memory bus based solution? So CPU only, talking directly to the storage.
Yeah, I mean, I think we could still apply these techniques in that case. And I think it would still provide us some benefits. Because we would still have more memory bandwidth probably at the memory controller level, and we would help offload some of the cost of the frequent flushes that we'll have to do from caches to make storage persistent that's on the memory bus. So I think there's still a benefit there.
Okay, thank you. And it's not, you're not relying on that being a third party outside of the CPU. In fact, you can okay,
yeah.
Thank you.
All right, let's thank the speaker one more time.